Okay, so last time we introduced probably what is the most important concept in the course, which is that of a topological space. And now we're going to see some more examples. So the first thing I want to talk about is metric spaces, which is a particular class of topological space. So let me remind you of the definition of a topological space, which I gave last time. So a topological space X is, let me say it this way, a topological space is a set X, and a subset U of the power set of X. So I'm going to state this definition a little different than I did last time. So this is the set of all subsets of X, the power set. So a topological space, it's X with a subset of the power set with the property that, well, first of all, X and the empty set are in script U. If U alpha is a collection of elements in script U for alpha in some index set A, then the union of alpha and A of U alpha, this is another subset of X, and this is also in script U. And then the last condition is if U1 up to UN, so if you have a finite collection of elements in script U, then their intersection is also in script U. Whoops, UN is in. Okay, so this is the definition of a topological space. So this set script U, these are the open sets, which is a certain collection of subsets of X, and that collection includes X, it includes the empty set, it's closed under unions, and is closed under finite intersections. So a remark is that, well, intersections of infinitely many open sets need not be open. So for example, minus 1 over n to 1 over n in R, if we say that's UN, these are open sets, but their intersection is just 0, which is not open. Okay, so we have these open sets here, these shrinking open sets whose intersection is just 0. Okay, right, so the main example of a topological space that I want to discuss here is metric spaces. And I'm going to introduce them with a specific example. So let's consider X the set of continuous maps from the interval 0, 1 to the real numbers. So real valued functions on the interval 0 to 1. So for example, f of x is x squared, g of x is sine x, h of x is absolute value of x minus 1/2. These are all elements in x. So the elements of x are functions. And we're going to define a distance between two functions any f and g and x. Here f and g are not referring to these specific elements. So the function, so the distance dfg is defined as the maximum of the absolute value of f of x minus g of x for x in 0, 1. So the picture is looking at functions on this interval, 0, 1, which we could draw. So we can draw these according to their graph. So maybe this is the graph of f, and we have some other function g whose graph is something else. Let's see, let me do something like that. I guess it doesn't matter. But then, so the distance between f and g, well, the way we compute it is, well, for each value x, we look at the difference between f of x and g of x. And there's some distance between those values. And we look at this for all values of x. And we're looking for the place where this is the largest. So in my picture, it looks like maybe that's for this value of x here. And that's what we declared the distance. So we call this a distance because it satisfies the main properties of the distance function on Rn. So d satisfies same properties as the distance function as the, well, usual distance function on Rn. Namely, well, first of all, d of fg is greater than or equal to 0, just because it's a max of values which are greater than or equal to 0. And it's equal to 0 if and only if f is equal to g. Well, if f is equal to g, then it's obviously, this is 0 for every x. But conversely, if f is not equal to g, then f and g differ at some point, and then you can show that they differ on some interval. And so, oh no, that's not even necessary. If they differ, well, if they differ at some point, then this maximum is greater than 0. Yeah, okay, fine. The second property is that this distance function is symmetric. Which follows just immediately from this expression. And then the third property is the so-called triangle inequality, that which is this inequality here, which says that the distance between f and h is less than or equal to the sum of the distances between f and g and h, just like in a triangle. And this inequality follows from the triangle inequality for real numbers. Okay. Okay, so this is well, all right, so we want to go from having this distance function to defining a topological space on X. So we'll say, okay, so yeah, okay, fine. So we'll say U subset of X is open if for each F in U, there exists some R greater than 0 so that the ball of radius R around F is contained in U. So as last time, this is G and X so that the distance between F and G is less than R. Okay, right. Yeah, so we have U in X is open if for any point there's a small ball which is contained entirely in U. Okay, so this makes X into a topological space. Okay, so the space of continuous functions on 0, 1 can be thought of as a topological space in this way. And in general, there's a general construction that if you have a function D, which satisfies these properties here, then you can form a topological space by defining open sets precisely in this way here. So the terminology is that here D is called a metric, and XD is a metric space. And then, as I was saying, any metric space is a topological space with open sets defined as above. So note, the converse is not true. There are topological spaces which are not metric spaces, and we'll see an example at the end of today. And okay, so this is a general way to construct topological spaces. If you have a set which has a metric, then you get a topological space. And the most important example for us is Rn with metric, the usual distance. So metric well, okay, so the distance between X and Y is, which is also denoted like this, which is defined as the sum of well, okay, by this formula. So you take sum of the squares of the distance between the coordinates, and then you take the square root of that. Okay. All right, so we'll maybe see some more metric spaces as time goes on, but I wanted to introduce them now. Yeah, so that's all I want to say about that for now. Let's talk a little bit more about continuity, which we discussed last time. So let me remind you that for X and Y spaces, topological spaces, a function from X to Y is continuous if F inverse of U is open in X for any open U in Y. So the preimage of an open set is open. Okay, so now I want to give you some examples of continuous functions. Examples. So first of all, polynomials. So let's take P of X, something like this. So here, the AI, these are real numbers. So P defines a function from R to R. And P is continuous, which follows basically from calculus, because, well, products and sums of continuous functions are continuous. Continuous real valued functions are continuous, and so that's how you prove something like this. And similarly, polynomials in several variables are continuous. So for example, you know, something like R squared to R, XY maps to, I don't know, X squared plus XY minus Y plus 7 or something. Okay, so we have this example that's hopefully familiar. Another example is, so I want to revisit the example that I mentioned a few times ago, stereographic projection. So remember, this was a function from the two sphere minus a point to R2. And the claim was that this function was actually a topological equivalence. And part of that is that it's a continuous function. And so let's explain why it's continuous now. So let's recall how this works. So here's P. So you have the two spheres sitting in R3, and P is the north pole. And the way this function works is, if we're given a point X, then we draw a line from P to X, and that hits this plane at a unique point, which we call S of X. Okay, so we want to show that S is continuous. And We're going to do that using our definition. So both of these we're viewing as topological spaces given the topology that they get from R3. So maybe first it's, well, okay, so this is the topology I mentioned last time that you get for a subspace of R3. So remember that means that well, okay, so a subset of R2 is open if U is equal to, or sorry, V is equal to U intersect R2, where U in R3 is open. So this is the, and similarly for S2 minus P, this is how you get the open sets. And well, this topology on R2 sitting inside R3 is the same as the usual topology on R3. So I'll let you think about that. But okay, so what we want to do now that we understand the topology on these two sets is show that given an open set U, in R2, that the inverse image of U under S is also open. So proof. So let's fix U in R2 open. So we want to show that S inverse of U is also open. Okay, so sorry, let me label this for later when you're just looking at this. So this is like the subspace topology, which we discussed at the very end. I don't know that I called it the subspace topology. Right. So we want to show S inverse of U is open in S in the sphere minus this point, i.e. Find an open set R in R3 so that S inverse of U is equal to R intersect S squared minus, or the sphere minus P. Okay, because this is what it means for S inverse of U to be open. Okay, and here's what R is going to be. So R will define as the let me write it informally first. This is the ray spanned by P and U. So we look at all of the lines from P to a point in U, and that defines some ray. So we have some ray like this. Explicitly, we could write it as a set as, well, it's P plus its points of this form, X minus P, P minus X. I have to get the order right. Sorry, I forgot how this works. X, P, this vector is X minus P. Yes. Yes. Okay. So it should be x minus p here. So here x is in U. And t is greater than 0. So I think this is the right expression. Okay, so this is the union of all the rays from P to a point in U. Positive rays, so T is positive there. And this is an open subset of R3, which is not so hard to check that, you know, for any point in here, there's a small neighborhood, which is also contained in a small ball around such a point, which is also contained in here. And right, I mean, by definition of how this ray works, observe that this equality holds. Yeah, so maybe I'll let you think about that. Maybe let me not go further into details here. I mean, right, so I mean, S inverse of U is exactly all of the points on this ray that meet the sphere. I mean, since this is how this map is defined. Yeah, okay. Okay, so these are continuity examples. So this is a good example to see how to actually use this definition of the preimage image of an open set is open to prove a map is continuous. I want to do one more example, or let me call it an exercise, for working with this definition of continuity. So the exercise is a composition of continuous functions is continuous. Which is to say, if we have x to y to z, and f, yeah, these are f and g, and these f and g are continuous, then this implies that g compose f is also continuous. So let's prove this. This is not so hard. It's worth thinking about on your own. Maybe you could pause this and then try it and then come back. But let's do it. So let's take U in Z open, and we need to look at G compose F inverse of U. We want to show this is open. So by definition, what is this? So this is X in X, so that G compose F of X is in U, which we could rewrite as G of F of X is in U, which then we could write as, so this is G inverse of let's see, how do I want to write this? Am I writing this correctly? First do F, then you do G. Sorry, I'm just a little confused. So wait, so so let me write it this way. So the claim is that G inverse, or G of F, compose F inverse of U, this is F, the preimage, sorry, let me just write the expression. The preimage of G inverse U under F. Right, so let's see why this is true. So the right hand, so I've already written out the left hand side here. The right hand side, so G inverse of U, this is Y and Y, so that G of Y is in U. No, sorry, this isn't how I want to write this. I'm sorry. Forgive me. So F inverse of G inverse of U, this is X and X, so that F of X is in G inverse of U, which we could rewrite as X and X, so that G of F of X is in U. What does it mean for F of X to be in G inverse of U? That means that G of F of X is in U. Okay, and indeed these expressions are the same. Okay, so now the point is, sorry, I'm making this exercise too complicated. So G, if U is open, then G continuous implies that G inverse of U is open, and then F continuous implies that F inverse of G inverse of U. Since the inside is open, then this preimage is open. But then this is equal to G compose F inverse of U. Okay, so this is how the exercise works. Okay. Okay, so I want to do one more thing now, which is give some more examples of topological spaces. In fact, let me title this Topologies on R. So the main thing I want to get across is that a given set has many different topologies. So I'm thinking of, when I say topologies, that's the collection of open sets. So it has many different structures as a topological space. So let's think concretely about the case when the set is the set of real numbers. So let me just tell you some of the different, some different topologies which are interesting. So there's the standard topology, which we already know about. This is the topology that we mean when we don't make any reference to a different topology. So this comes from the metric. D of xy is just the absolute value of x minus y. Okay, but there's others. So there's the discrete topology, which is a topology that exists on any set, topology, in which we just declare every subset is open. So this is a topology because, well, it just satisfies the properties. X and the empty set are open. Unions are always going to be open because every subset is open, and intersections are always open because every subset is open. So that's a topology. So in particular, note that here, the singleton is open. So this is a difference between the standard topology and the discrete topology. I mean, of course, in the standard topology, it's not the case that every subset is open. For example, single point sets are not open. Okay, so this is a different topology. There's another topology that you can define on any set, which is called the indiscrete topology. Which the only open subsets are X and the empty set. So in any topological space, we insist that X and the empty set are open, but in the indiscrete topology, we say that's it. And this is a topology. And you can just check the axioms hold for this example. Let me tell you about one more topology, which is the cofinite topology, which is a bit more interesting. So here we say that U in R is open if the complement is finite. Okay, so an open subset looks something like this. So there's some finite set of values that are omitted, not in U, and then U is the rest. So this is how an open set looks in this topology. And yeah, so notice, for instance, that, well, yeah, I mean, this is different from all of these other topologies. So in the standard topology, you have open sets, which are intervals like this, but an open interval like this is not open in the cofinite topology because the complement of this open interval, it's not finite. I mean, it's uncountable. Okay, so yeah, I wanted to say a couple of things about this topology. So let me make space. Oh, come on. Work with me here. So a few remarks. So first of all, well, this topology, it might seem like a strange topology to put on R, and in some ways it is, but in other ways it's a natural thing to do. So the remark is this is an example. Well, okay, so this is an example of the Zariski topology in algebraic geometry. So the connection is, well, a finite set, if you look at polynomials, well, okay, I don't know how much I want to say about this. I mean, the thing is, if you look at a polynomial on R, it has finitely many roots. And the complement of such a finite set, you know, the zero set of a polynomial, that's an open set in the Zariski topology. Okay, this is just meant to be a side comment. This is an interesting topology in algebraic geometry, a particular instance of it. The other thing I want to say is that this topology is not induced from a metric. Which is to say it's not a metric space. There's no metric. So, right. So at a few slides ago, I said, if you have a metric space, then you get a topological space, but it's not necessarily true conversely. Not every topological space comes from a metric. And this is an example. So let me explain why this is true. So this follows from two observations. So the first is, if X D is a metric space, this is a general statement, then for any P and Q distinct points, so let me say P not equal to Q in X, there exist open sets U containing P and Q containing, or V containing Q, so that U intersect V is empty. And the proof of this is not so hard. Let me do it up here since I'm low on space. So we're in a metric space. We have 2 points, P and Q. I want an open set that doesn't contain either of them. So first, let me take R to be the distance from P to Q. And let's look at the balls of radius, I don't know, R over 4 or something. Those balls are going to be disjoint. So that's what I take as my U and V. And you could take, I mean, there's different choices, but we just want an example. Okay, so this is a property of metric spaces, and this property has a name, which is Hausdorffness. So metric spaces are Hausdorff. There's not enough space here. Hausdorff, 2 Fs. And then I'm off the page, sorry. Okay, but then on the other hand, okay, so this is a property of metric spaces. So if you want to show a space is not a metric space, it's enough to show that it doesn't have this Hausdorff property. So in R with the cofinite topology, for any open sets U and V, the intersection is non-empty. And this is not so hard to see because, well, the intersection is open. Well, sorry, I mean, this is not so hard to see. I mean, you have two subsets whose complement is finite. You intersect them, the complement is going to be finite still, because it's still an open set. And so then the complement's finite, so they can't be all of R. I mean, if this is empty, then U intersect V complement is R, but U intersect V complement is finite. And R is not finite. So that's the reason. And I'm really making a mess here now. But summary, these two facts together tell us that R with the cofinite topology is not induced from any metric. Okay. Okay, so I think I'm going to stop there. Yeah, so next time we're going to talk about surfaces and topological equivalence for surfaces.